Okay, class, so this is the final content for Module 6, and it essentially deals with the process of estimating runtime for certain types of algorithms. So let's take a look at this. So estimate the runtime for some types of algorithms. Let's consider linear time. So suppose I give you the following code snippet. Int count equals 0, and that we have a for loop for int I equals 0, I less than, say, a dot length, I plus plus. Okay, where a is an array, and we're basically doing a search for in this particular algorithm, we're counting the occurrence of a particular element in an array. So for instance, we suppose I have an array of 10 or 100 numbers, and I want to count the number of times that 7 occurs in an array of 100 numbers. So this for loop I started here, and we'll finish now, will do the job. So if AI, so if element I happens to equal to value, which I said was 7, then we'll increment a count, like so, okay? So here's a for loop which would count the occurrence of 7 in an array of 100 numbers. So what is the running time in terms of n, the size of the array? Okay, so we visit each element once. All right, if each visit consists of a fixed number of actions, then a loop with n items has big O in running time. Okay, and that's the case here. So each visit consists of incrementing a counter. So that's a fixed number of actions. This works even this estimate, I should say, applies even if the loop terminates early. Okay. All right. So this is called linear time. There's another estimate for the runtime of an algorithm that's called quadratic time. So let's see what quadratic time is all about. So quadratic time. Quadratic. Did I misspell quadratic? Quadratic time. There we go. All right. For quadratic time, okay, so consider using the previous loop example, but this time each iteration performs a lot of work. Okay, so suppose we want to find the most, okay, so an example of this is suppose we want to find the most frequent element in an array. Okay, what is this called? The mode? All right. So we have something that goes like this. We have element A1, A2, A3, so forth. Suppose it's a 1 million element array. A10 to the 6 over 4, okay. A10 to the 6 over 2, and then finally A10 to the 6. So we have a 1 million element array, and we want to find the most frequent element. Okay, and so turns out that the counts are something like this. A1 occurs once in the array. Element A2 occurs 3 times in the array. Element A3 occurs twice. This particular element also occurs twice because it's the same as A3. Say this element occurs 3 times, and say this element occurs 4 times. Okay, so that's kind of our contrived array in the account. So what we want to do is calculate the most frequently occurring element. And so here's what we can do. First thing, for step A, for each element in the array, compute the count of how many times it occurs. Okay, so that means you visit each element and you count how many times it occurs. Okay, that's all you do. So you make 1 million visits, and at each visit you count the number of times that element occurs. Okay, so step B, compute the maximum of all counts. Right, and then step C, find the maximum in counts. Okay, all right, so okay, so what's going on here? All right, so this loop excuse me, that should be the maximum in counts. All right, so this loop has n iterations. With each step taking big O in times. So for this algorithm, we have big O of n squared. Okay, all right, so quadratic time. So this is why it's called quadratic time. Okay. Okay, so let me give you an example. Go on to the next page of what I mean by this. All right, suppose we have an array A. So A, with the given elements, what do we have? Say 8, 7, 5, 7, 7, 5, and 4. Okay. And then we compute our counts for each element. And we have 1, 3, 2, 3, 3, 2, and 1. All right. So the maximum of counts is equal to 3. Okay, and then we look where 3 occurs. Okay, so next we look up where 3 occurs in the counts and find the corresponding values. Okay, and so this happens only at 7. Okay, so that's how this works, and it's a quadratic. It's of order quadratic. All right, now this brings up an interesting point. Suppose we have an algorithm, some arbitrary algorithm, don't know what, that executes in 3 phases. Okay, so the first phase has a determination of we'll call it T1. The first phase execution, it was found to have an execution time that is modeled something like this. Okay, then the second phase of the algorithm was found to have an execution time somewhere of an order like this. And then the third phase was also linear. Let's see, F times N plus G. Okay, so the total estimated runtime is equal to the sum of the 3 estimates. Okay, so the runtime estimates are additive, but that isn't the case for the estimate of the order of the runtime for the algorithm. The algorithm's runtime is still second order, right? Okay, which is still big O of n squared. So order estimates are not additive. Okay, that's one of the takeaways of this particular note. Okay, so let's discuss now perhaps an alternative to computing the mode or the most frequent element of an array. In this case, we visited each element and then we basically counted how many times it occurred in the whole array, which seems somewhat wasteful because perhaps there's an alternative way of doing this, and there is, and this is called the triangle pattern. And we would like to know if the triangle pattern can reduce the order from quadratic order to some smaller order. All right, so let's investigate that. All right, so this is called the triangle pattern. Okay, so the preceding algorithm used repeated countings of the same element. Okay, before counting AI, the ith element AI, okay, should we first check that it didn't occur in the preceding elements. Okay, so let's estimate the cost of the additional checks. So in the ith step, the amount of work is proportional to I. Each step takes big OI time. But this is still the same as big O of n. Hence, this alternative pattern of visiting elements in a triangular fashion pattern is still n squared. So you don't gain anything by not revisiting the elements each time. So in this triangle pattern, you don't revisit the elements and searching for the most prevalent element. In the preceding algorithm, you did, and so there's no gain, interestingly enough. So let's look at an alternative, a final alternative, and let's examine algorithms that use logarithmic time. Okay, so these algorithms arise from programs. Let me reword this. Let me rephrase. Okay, logarithmic time arises from algorithms that cut work in half at each step. Okay, and these would include binary search and merge sort. Okay. All right, so let's see here. Consider an algorithm for finding the most frequent element. Just like before, like with the triangle pattern. All right. Let's sort the array before counting frequencies. All right. So the sort, of course, sort occurs in big O, n log n time. All right. So for instance, well, I guess I should go on to the next slide. I'm out of page space here, so let me go on with an example. So here's my array. So my array, all right, consists of unsorted 8757754. Okay, and then when you sort it, we get what? 4557778. Okay, and then our counts on the sorted array would proceed like this: 4557778, and then our counts would be 1, 1, 2, 1, 2, 3, and 1. Okay, so it's a little bit different way of dealing with the counts. And so the pseudocode would proceed something like this in Java. So let's initialize our count to 0. All right, and again, we'll have a for loop. I less than a dot length. Okay, and so what do we have? Increment count. Okay, and if I is equal to the length minus 1, or AI is not equal to the next element, okay, then what do we do? I'll indent for readability. Okay, we increment our counts. Okay, and then we set count back to 0. Okay, so you can see then that the count is kind of like an accumulator for the number of elements which are alike. Okay, and then when the next element is different, we bump count back down to 0 and restart the accumulation. Okay, and this happens after the sort. Okay, so so the observation here is that each iteration requires a constant amount of work. In other words, there's no looping going on in the iteration. Thus, each iteration is linear. Although we visit 2 elements. Although each pass requires 2 visits. Thus, the big O of this particular algorithm is O n log n. So this is the way you would want to count the frequency of elements in an array. Okay, enough said.